This first problem is quite quagtastical. It asks us to determine what it asks us to use the ideal gas law to calculate the volume of 1 mole of an ideal gas at STP. We should remember that standard temperature and pressure are 1 atmosphere and 0 degrees Celsius, which is 273.15 kelvins. The ideal gas, and the ideal gas constant is, of course, 0.08206 liter atmospheres per molk, or mole Kelvin. It's asking us to determine the volume. I've got the per vert equation, PV equals nRT. I'm going to rearrange it algebraically to put V on one side and everything else on the other. You should remember from an earlier lecture that I mentioned that all ideal gases, it doesn't matter if it's oxygen, carbon dioxide, it doesn't matter if it's fart. They occupy at standard temperature and pressure 22.41 liters. All we're doing here is trying to take these numbers and see if that mathematically checks out. So I throw in my number of moles, 1 mole, my ideal gas constant, 0.08206 liter atmospheres per molk, and my temperature, which is 273.15. You can once again see why we don't use degrees Celsius here, because if we had 0 degrees Celsius here, it would make the numerator 0, and that just wouldn't make sense. In the denominator, we have pressure, which is 1 atmosphere. We should see, of course, that our units cancel out beautifully. I've got atmospheres killing atmospheres, moles canceling out moles, kelvins canceling out kelvins, and I'm left with liters. If you throw that in your calculator, you should see that it equals 22.41. Aren't we having a grand old time? And this question asks me to calculate the number of molecules, so number of molecules in a deep breath of O2, deep breath of air whose volume is 2.25 liters and whose temperature, at body temperature, 37 degrees Celsius, and pressure is 735 torr. So there we go. Okay, so once again it's asking number of molecules. I'm going to throw down my per vert equation, PV equals nRT, the ideal gas law. I've got pressure, I've got volume, I've got my ideal gas constant, I've got my temperature. Is number of molecules embedded anywhere in this? No, it's not. But is there anything in this that I can use to eventually obtain number of molecules? Yes, there is. It's N, which is number of moles. So what I'm going to do is I'm going to rearrange this algebraically to put moles on one side and everything else on the other. Moles equals PV divided by RT. Now I have to make sure my units match. The ideal gas constant is 0.08206 liter atmospheres per mole Kelvin. I've got atmospheres. Oh, I don't have atmospheres, I've got torr. So I'm going to have to convert. I have to remember that I've got torr in the basement, I've got atmospheres on top, and I have to remember that 1 atmosphere equals 760 torr, something I require my students to memorize. I also have kelvins right here. I don't have kelvins over here, so I'm going to have to do that conversion. 37 degrees plus 273.15 is going to give me my temperature in kelvins. When I did that conversion earlier, I determined that, this temperature equals 310.15 kelvins. I also determined that the number of atmospheres here is 0.967 atmospheres. All my units match now, so I'm good to go. Number of moles is going to equal pressure. Pressure is 0.967 atmospheres multiplied by volume. Volume is 2.25 liters in this case, divided by the ideal gas constant, 0.08206 liter atmospheres per mole Kelvin, multiplied by temperature, and temperature is going to be 310.15 kelvins. Kelvins cancel each other out, liters cancel each other out, atmospheres cancel each other out. I'm left with moles in the denominator of the denominator, which means it's in the numerator, so that should be a number of moles. I did this calculation earlier, and I determined that N equals something. Yeah, equals 0.0855 moles. Now the question isn't asking us to determine the number of moles, it's asking us to determine the number of molecules. I'm going to write down 0.0855, and it's just saying in a breath of air. A breath of air is not comprised of a single pure gas. It's got lots of different gases in it. Oxygen, nitrogen, hydrogen, even some trace amounts of helium, argon, and other things. But that doesn't matter. I know the number of moles of gas. Can I convert that into molecules? I think I can. You should remember, of course, that 1 mole is equal to 6.022 times 10 to the 23rd molecules, which is a very long word. I need to make sure to give myself room there. This is Avogadro's number. Moles cancel each other out. I'm left with molecules as my units. I throw that into my calculator, and the final answer ends up being 5.15 times 10 to the 22nd molecules of air.